Hello everybody, welcome to chapter 3. I want to start off before we dive into this chapter, so to see how you can explain how this is going to be broken down. So chapter 3, here's that, page 3.0. Chapter 3 kind of talks about ionic compounds, what are their properties, and you're going to see something about that in an experiment. Then we're going to talk about monatomic ions. That just means one atom at a time with a charge, like we sort of saw a little bit in chapter 2. And then we're going to talk a little bit like, well, how do we know what the charge is? What do we call these things? And that's going to be the first half of chapter 3. The second half of chapter 3 is going to be putting together some more complicated ions together into compounds. How do we name them? How do we write the formulas for those? And then we're going to take just a little look at acids and bases at this point, because it's a nice place to look at that in chapter 3. Okay, now I've warned you about this. I'm going to lower this camera a bit. I've warned you about Chem 51 being a course that continues to build on itself. So already here we are in chapter 3, and I'm saying, oh yeah, by the way, you better know all your symbols and names for the elements. You better be able to recognize metals versus nonmetals, main group transition metals, write electron configurations, and identify valence electrons. If any of those things are rusty, I strongly recommend that you stop, go back and look at chapter 2 and kind of pick those things up. Okay, there's the big picture. Now, right off the bat, how do we even identify ionic compounds? Now, I've got this group here of ionic compounds, and I have this group not ionic compounds. This is really going to be chapter 4. That's okay for us for right now. So what I'd like you to do is stop the video, or I'm going to put a little quiz here in the video. Stop the video with your lecture mates and say, what do all those ionic compounds have in common? All right, you either stopped and chatted, or you answered the video or answered the quiz that I stuck right into the video. And you're saying, gosh, sodium, iron, silver, nickel, titanium. I'm remembering that from chapter 2. Chlorine of some variety, oxygen, hydrogen, oxygen, fluorine, maybe sulfur. This sulfide, we've never heard of that, but you go, well, it sort of sounds like sulfur. So you said, oh yeah, for us, for Chem 51, we're going to say at least one metal and at least one non-metal. So say at least one metal and at least one non-metal. Now, everything's more complicated than that, but that's a really good place to start. That'll get us 80-90% of the time. That's the only rule. Now there's one other thing we're going to sneak in here that we can't really define until chapter 4, but that's okay, we can recognize it. I've got 4 other compounds written here. Same thing, either answer the quiz questions that I put into the video, or stop and chat with some friends and say, gosh, what do those all have in common? Well, you saw it, right? You said, I don't even know what this is. But you said, you know what? There's an NH4 there. There's an NH4 there. NH4 there. NH4 there. So our first rule is there a metal and a non-metal? Yes, it's ionic. The other thing is, do I have this NH4? I'm sorry, I got a little disorganized with my notes here. Or NH4. Oh, I'm going to leave that off right there. Now, that's actually NH4 plus. But that's okay. All I have to do right now is say, is there an NH4? That's going to be ionic. Okay, now, the other big picture, I want to talk about the structure of ionic compounds. So I put together a little video that says, well, what if I take sodium ions and chlorine ions and put them together in a gas phase? What happens? So I'm going to go to that, and then we'll come back. Start us off here. I've put some ions in a container. The red ones are sodium, +1, and the blue ones are chlorine, chloride, -1. And what we're going to do is just let them move about naturally and just sort of see what happens to these ions. They were in gas phase. We let them go. They're bouncing around. And let's just see what happens. And I don't know about you, but when I'm watching this, I had this sense of like cheering them on. Like, come on, cations, come on, anions. You can do it, you can do it. So even now you can see like that little squarish thing in the right there. Oh yeah, that thing's kind of organized now. Let's watch what happens. We get them all to come together. And you can see it's pretty obvious. Nature is just naturally going to organize these things into this structure. And this structure is the basis for all ionic compounds that we're going to see in chapter 3. All right, hopefully I edited that smoothly and you saw the video and you said, oh yeah, that's kind of cool what ionic compounds do. And I've got this sort of oversimplified drawing here. And remember what we saw was the little sodium ions. There they were. And you can see this is idealized. The animation was messier and more real, but that's okay. We're saying, okay, this is... And I've got those chlorides. That's chlorine with a -1. So that's a little bit idealized. But like, oh, okay. And the question is really, is there a pattern? Well, yeah. And we usually call this a lattice. It's like if you went to Home Depot and you bought, that lattice to put like a fence up in a garden. And so you've got this sort of crisscross pattern. So we'll say yes. And the term we use is lattice. Now, sometimes students think it'd be like oranges all stacked up at a supermarket or something. And it can be, but you can see, like, do the ions have to be the same size? Well, they could be, but do they have to be? No. We'll say they may be same size, but not always. Now, here's a big idea. Count the chlorine minuses, we call them chlorides. Count the sodium pluses. Give me the total charge on this little chunk right here. And you said, well, gosh, it looks like there's 8 of those sodiums. That would be 8 plus. But it looks like there's 8 of these chlorine chloride things. That'd be 8 minus. Oh. 0. This is huge. The total charge on any ionic compound is always 0. Now, the sort of macroscopic structure and macroscopic properties and microscopic structure, this will come from the experiment that you're going to do this week. So I'm going to maybe come back to this in lecture 2. But what I want to do right now is think about what is the structure? It's opposites attract. Professor Paula Abdul says you put a bunch of pluses and minuses and they will stick together. Those bonds are, as you saw, although there was some wiggling, once that structure settled down, it was kind of it. I mean, it's kind of wiggling around, but you could see, like, that was it. The thing wasn't going to sort of be disrupted. Let's see. Let's do this. So the first ionic compound, I want you to see that in the experiment. The second thing I'm going to say, you won't see in the experiment. If they're strong bonds, but they're very inflexible, you can imagine, take a crystal of salt, hit it with a hammer. Does it flatten out nicely like a piece of metal? No, it shatters. So these strong and flexible bonds mean if you hit this thing, it's going to break up. Now, I have a really lame animation. Well, it's not even an animation. I'm going to do this. Well, let's do this one more thing. I'm going to, this other thing here, you're going to see in the experiment as well. So I don't want to give away the first thing. I don't want to give away this other thing, but I want to give you one hint. Water is not ionic. Hydrogen, oxygen, there's no metal in there, so it's not an ionic compound. But strangely enough, if I sort of think of it like a couple of atoms stuck together, what I get is this charge-ish thing. I get sort of a plus there, and I get sort of a minus over here. It's not a real charge, so we do this funny little delta plus, delta minus, which might give you a hint that would water interact with ionic compounds? And the answer is, yeah, it will. Okay, you're going to see that from the experiment, and then we'll come back and review this. I'm going to pause it and get a pair of scissors, if I can find the right button. Ah, there it is. All right, I'm back. Sorry, I had to go do some fine-tuning on my computer because this next animation takes such incredible computing power. If I didn't get this set up, it just doesn't work. So here's my very high-tech, I've got 4 computers running this right now. So what we could see is like, oh, there's a chloride, negative, plus, plus, negative, negative, plus, plus, negative. So Professor Paul Abdul says you had these things would stick together. Now imagine I hit this thing with a hammer and I smashed this down like that. Now I've got plus, plus, minus, minus, plus, plus. Boom, it just flies apart. Why are ionic compounds brittle? Well, if you hit them and get everything to shift over, all of a sudden we've gone from attraction all the way through to repulsion, and they go apart. Do you see how high-tech that was? My smoke is coming out of my computer. It took so much computer power to demonstrate that. All right, how do we get to ions? Well, we need to look at that, because if we know how atoms get to ions, then we're going to be able to predict, well, what kind of ions are they going to form? And then that'll allow us to say, well, what might become ionic compounds? So we've got to think about a couple of things here. I've got a lithium atom, and what I want to imagine, it's losing one valence electron. So lithium is atomic number 3. There's lithium. 3 electrons, 3 protons. Now over here, it's going to lose one of those electrons. So I'm going to go 2 electrons, 3 protons, lithium, and there's my charge. And I go, oh, well, yeah, if you lost one of those electrons, and I'll just put the electron over there. So there's forming a lithium ion. It loses 1 electron. That's what we get. Okay. Similarly, what about if oxygen gains 2 valence electrons? Well, oxygen is what? Number 8. So there's oxygen. And I'm going to add 2 electrons to it. So now I've got 10 electrons and 8 protons, because it's still oxygen. What's the formula? What would I write for that symbol for that ion? Well, it's got 2 more electrons. O2 minus. Similarly, aluminum loses. Aluminum is number 13. There's aluminum. Loses 3 electrons. So I'm going to put them over on the right. Like they were there, but they're gone on the other side. And I've got aluminum. If it loses 3, it's down to 10 electrons. 3 plus. Okay, that's how they get there. They either gain or lose electrons. So what we want to be able to do is say, well, can I predict who would gain or lose electrons? Even better yet, can I predict how many an atom would gain or lose, and I can predict the charge, and then the whole thing is, we understand how everything works. Remember, I love this stuff. All right, and I'm just reminding you, or remember the ion is the number of protons minus number of electrons. That gives me the ion charge. And we have 2 new terms. If something is positive, we call it a cation. If something is negative, we call it a dog ion. No, I'm joking. We call it an anion. Now we just have to have that language. I have to immediately know what that means in the charge. I have a silly way to help me remember it. If I cation, that looks like there's cation with a plus. And if I do anion, that helps remember. Cation, anion. Just have to memorize it, have to know that, the charge, what it means. That's part of our language. Okay, now, let's start looking at our first sort of evidence and examples of what's going on here. I've given you 6 neutral atoms in the electron configuration that we did in chapter 2. This is page 3.5, by the way. And I'm saying when sodium becomes an ion, it's always +1. And there's its electron configuration. Calcium always becomes +2. Aluminum always becomes +3. Now we're saying 3 plus, 2 plus, 1 plus. It's a technicality. I don't really care which way you say it. The book may require you, or the homework will probably say, well, in chemistry, we're going to talk about ion charges as the number and the sign. So a number and then plus or minus. I'll flip back and forth. Nitrogen, when it forms an ion, is always 3 minus. Sulfur is always 2 minus. And fluorine is always 1 minus. Now, can you see, if you stop and look at the video and say, how did sodium go from this to this? What changed? How did calcium go from this to this? If you know that, then what would you predict for aluminum? I've got a hint for you. Let's think about valence electrons. Remember, that's where all the action happens. Valence electrons are where all the chemistry happens. So I'll look at sodium and say, well, there are the valence electrons. Calcium, valence electrons are 4s. Aluminum, they're right there. Now, if I look over on this side, that used to say 3s1. This used to say 4s2. This used to say 3s2, 3p1. And what I've got left over here, 1s2, 2s2 electrons, 2p6, and that's it. Now these next 3 atoms don't form cations, they form anions. So I'm showing you nitrogen becomes 3 minus because it gains how many electrons? 3. Sulfur is going to gain 2 electrons. Fluorine is going to gain 1 electron. So how did nitrogen go from nitrogen, the neutral atom, to nitrogen with a 3 minus? How is sulfur going to go from sulfur to sulfur 2 minus? How is fluorine going to go from fluorine to fluorine minus 1? How many electrons did nitrogen gain? 3. Where did they go? Oh, I used to have 2p3. Now I've got 2p6. If sulfur picked up 2 electrons, what would the electron configuration be for the ion? I'm either going to put in a little quiz in the video right here, stop and answer the question, or stop the video and chat with your friends. Go, wait, how did nitrogen get to be 3 minus? What's that electron configuration? How did sulfur get to be 2 minus? What's its electron configuration? All right, you pause the video, right? I'll wait. No. All right. So sulfur picks up 2 electrons. 1s2, 2s2, 2p6. And I go to those valence electrons. 3s2 is full. 3p6. Took on 2 more. Fluorine, similarly, 1s2, 2s2, 2p5 becomes 2p6. Now, hopefully you're saying, wait a minute, on those ions, I'm seeing a pattern. But before we jump to that, I want you to go in this little bit of the periodic table, and I want you to write the charges for, what have we got here? Write the charge for sodium, write the charge for calcium, write the charge for aluminum, nitrogen, sulfur, and fluorine. Just literally write the charges on that periodic table. Stop the video, chat with your lecture mates, and say, any pattern, anything interesting there? You did it, right? And you said, whoa, 1 plus, 2 plus, 3 plus, 1, 2, gray area, 3. It looks like maybe nature's given us a break. If I over go to nitrogen here, 3 minus, sulfur, 2 minus, fluorine, 1 minus. Whoa! Now, there's a hint. Now, do these stable ions have anything in common is the last question on the bottom of this page. So I start looking at all these, and I go, okay, well, 1s2, 2s2, 2p6. Okay, 1s2, 2s2, 2p6, 3s2, 1s2, 2, I go, wait a minute. S2p6, 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 even the anions. Whoa! Nature has given us a big hint here, a big clue. All these ions that we're looking at, all ions in these examples, go to S2p6. Whoa! What's 2 plus 6? Get your calculator out. 8. Would you be surprised if we said, well, octet's sort of another word for 8? We sometimes call this the octet rule. It's a hint that nature's saying, you know what I'm going to do? I'm going to gain or lose electrons. If I'm an atom, I will gain or lose electrons until I reach a certain configuration, which, oh, by the way, happens to be 8 electrons, S2p6. Whoa. All right. Let's look at the next page. So it says, put my electron dots for selenium. Se, barium, bromine. And then it says, do the electron dots for the ions that are formed. So I have to go over there and go, okay, now wait a minute. Selenium, that is right below sulfur. What do we know about elements that are in the same column on the periodic table? They have similar chemical properties. So would you be really surprised if I said, we said, gosh, on that other page, sulfur becomes S2 minus. Would you really be surprised if I told you that selenium becomes 2 minus? I'm going to put on my electrons. 1, 2, 3, 4, 5, 6. And then it says selenium. And it says add 2 more electrons. Two minus. Whoa! Now the simple symbol, 2 minus. Can you do the same thing for barium? And barium is in the same column as calcium, so you can guess what barium's charge probably going to be. Can you write the symbol there? Now that one's a little bit tricky. Bromine is in 17 or 7A. We know it's got 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. Bromine's in the same column as fluorine. Fluorine was -1. We're going to guess bromine is going to be -1. Go ahead and finish up those two. Pause the video. You pause it. Everybody agreed? You go, oh, this looks a little bit funny. Those electrons are gone. Bromine, that's what it had. And we said, oh, it's going to become a -1. So sometimes what we do is we put this 1 minus, this 2 plus, this, sort of to show like, well, there's some electrons have been added or removed, and there's the charge, and there's the symbol. Magnesium, similar to calcium. Now just the symbol. No dots, just the symbol. 3.2 says sulfur atoms gain 2 electrons. Write the symbol of the ion that's formed. We just did that on the other page. Was it a cation or an anion? Yeah, we just did that on the other page. This is an interesting one. This says, write the electron configuration of potassium. By the way, what's going to behave similarly to potassium? You look in that same column, look at the other page. Is there anything that's similar to potassium that you could predict? And then it says, what could you do? How could you change that electron configuration so that it ends up with S2P6? Could you pull off some valence electrons or put on some valence electrons? Is that going to form a cation or an anion? And then you're going to write the symbol with a plus something or minus something. Okay, this one we did on the previous page. Okay, that's a hint. That one we did on the previous page. That one we did on the previous page. I'll do 3.4. You pause the video, chat with some lecture mates, and then come back. Okay, you did it, right? Potassium, you say, okay, 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. There's potassium. What's the easiest way for potassium to get to an S2P6? Well, it sort of has it right here. What's the easiest thing for it to do? Lose that one electron. If it loses one electron, what's its charge? Plus. Cation or anion? Cation. Okay. So now we have this, this is so cool. We have this power to look at any element on the periodic table. We know hardly anything, but right now I can go, oh yeah, I can tell you, I can make a pretty good guess about the charge most of the elements are going to form when they're in an ionic compound, which is just cool. All right. Now, if we go to page 3.7, here's the summary. We've been hinting at it, sort of showing some examples, and now we can go, oh, look at those guys. Plus ones. 1 plus, 2 plus, 3 plus. Right on the periodic table. I have to memorize it. Oh, 1 plus, 2 plus, 3 plus. Then there's all this gray. The gray means, not always sure. So let's go over here. 1 minuses, 2 minuses, 3 minuses. Now there's a little bit of a weird thing here, but I go 1 plus, 2 plus, 3 plus, 3 plus. There's 3A. 3 plus, 2 plus, 1 plus. So there's a little predictability region there. 1 minus, 2 minus, 3 minus, 1 plus, 2 plus, 3 plus. Because we know that they're gaining or losing electrons to get that S2P6, which is what these guys have. So why don't we write charges over there for helium, neon, argon? They don't do this. They're already, helium's S2. Everybody else is S2, S2, P6. They're done. They're not going to gain or lose electrons. Okay, now, there's this fuzzy area that gives us a little bit of heartburn. But if I look at these common metals, chromium, magnesium, iron, copper, mercury, tin, and lead, is there anything you could put on your flashcard that would at least help you? If you have to make a guess, these 8 elements, you're like, they're weird. They have more than one possible charge. What would my flashcard say that would get me most of the time? How about 2 plus? 2 plus, 2 plus, 2 plus, 2 plus, 2 plus, 2 plus, 2 plus. Oh, now, in here, yeah, copper's 2 plus, but sometimes it's 1 plus. Come on. All right, there we go, camera. But sometimes it's 1 plus. Look at silver. Silver's always 1. You go, oh, that'd be a good guess for copper. Well, let's skip that one. Let's get rid of it. Now, Mercury doesn't exist. Don't worry about it. Over here, we did this kind of like 1 plus, 2 plus, 3 plus. If you had to guess any pluses in 4a, what would you guess? 4 plus. 1 plus, 2 plus, 3 plus. Oh, 4 plus. 4 plus, 4 plus. So these 7 or 8 elements, yeah, we just have to memorize them. There are all these nice patterns. We have to memorize some, but even those patterns hint about these gray area metals that can have more than one charge. So it's not that bad. All right. Let's go back and look a little bit more. Now we've seen the patterns. We can sort of start to make some predictions, but we can fine-tune that. Things don't just gain electrons or lose electrons, and it's all the same process. There are subtleties. Some elements really want to gain, some sort of want to gain. Some really want to lose, and some they'll kind of lose, or maybe you really have to fight them to get them to lose electrons. So let's look at this in a little more detail. I said, here's lithium, and we said it loses an electron and becomes lithium plus. It doesn't naturally do that. It will not. Lithium won't just sort of spontaneously lose an electron. What I have to do is add some energy, slam it, hit it, do something to that atom. So lithium plus ionization energy that's some amount of energy to knock that outermost electron off. Lithium plus ionization energy gives me the lithium ion, and there's that electron that's been bumped off. So more precisely, we'll say ionization energy is the energy required to remove the outermost electron. It takes some energy to remove an electron. So we'll say, well, maybe we can compare atoms based on how much energy it takes to remove that outermost electron. So we can say, well, if I find one that has higher ionization energy, it requires more energy. It's more difficult to remove or lose that electron. And we're going to be able to use something in chapter 2 and make a whole bunch of cool predictions. Now, the other way around, strangely enough, most atoms will take on one more electron. Opposites attract. There's some room out there in an outer shell. Most atoms will actually take on an electron. So let's define that. Here's fluorine. Takes on an electron. Becomes fluoride, F-1. Well, if you have, what if you really like to collect something? Like, I like to collect bikes. I'm silly. I got a whole garage full of bicycles. I love bicycles. I keep collecting more bicycles. I have an affinity for bicycles. I love those machines. Well, we have this. If I take fluorine, I add an electron to it, fluorine becomes -1, and it actually releases energy. It's so happy it gets to go to a lower energy condition and lose some energy. Remember, nature's being lazy. That energy it loses is electron affinity. That's sort of like the happiness released when an element, an atom, gains an electron. So, I'm going to say here, electron affinity EA is the energy released when an atom gains an electron. So higher electron affinity means there's a greater tendency to add or accept another electron. So we could say things that have high ionization energy, they don't want to give up electrons. It's very difficult to get them to give up electrons. Things that have high electron affinity, they love to take an electron. So, okay, now I'm going to think about this. Have you ever played with magnets? When you put magnets close together, they really stick. get them far apart, it's like there's no force between them at all. But you get them close. So you get two magnets that are far apart, pretty easy to separate them. You get magnets that are close together, and it's harder to separate them. That's my analogy. The closer an electron is to the nucleus, the more tightly it's held. It's difficult to remove it. Or the other way to think about it is a nucleus would like to grab an electron and pull it in close. So we can think about this. The smaller atoms, the electrons are closer to the nucleus. Does it require more energy or less energy for a smaller atom to remove that outside electron? Small atoms hold their electrons tightly. More energy to remove an electron. So now we can go back to chapter 2 and think, well, wait, what do big atoms do? What do little atoms do? And we can start to make some predictions. Now, smaller atoms, they're happier to gain an electron. They get to have an electron come in really low energy and come in close to the nucleus. So they release more energy when an electron is added. So small atoms don't want to lose their electrons, but they kind of actually like to gain some electrons. Big atoms, that's relatively speaking, right? They're all small, but bigger atoms, their electrons are way out there. They barely know they're there. They'll lose them. They'll just fall right off. Can you add one to it? Maybe. It doesn't really care. If the electron's out at the 4th or 5th or 6th level, it doesn't even know it's there. Okay, now, let's go back to chapter 2 then. Remember this little fib? It's a pretty good fib. It's not exactly right, but it's pretty darn close. We said when we go down a row, new shell, 3rd, 4th, 5th, 6th, the shells get bigger. Going across here, they're in really the same shell, but more protons means as I go from like calcium or potassium, calcium, scandium, titanium, vanadium, chromium, that more and more protons in there keep pulling it in so they get smaller. Okay, now here's what I want you to think about. There's a pattern here you can see. Who is going to lose electrons most easily? Can you sort of say a region? Left, right, top, bottom, anything? One corner, one row, one column? Which of these elements is going to lose an electron most easily, have the lowest ionization energy? I'm probably going to pause the video right here, put in one of those little quizzes. If I didn't, stop the video and think, well, who's going to lose electrons most easily? How about those guys? And you could even say, well, they're the biggest atoms on the periodic table. They would lose electrons, no problem. So let's say lower left. That's the place where those things will just lose electrons easily. Now, where are the really tiny electrons that would love to just grab another electron? How about here? Those little tiny atoms can't pull an electron off, but they'd be happy to take on an extra electron. So we go, oh, lower left, upper right. Now, there's a whole column I chopped off of this thing because it doesn't really have anything to do with this. What was over here that I've just not even put on this chart? The noble gases. They had that S2P6. That's it. They don't want to do anything more. That's as far as they don't go anywhere. They don't want to gain or lose any electrons. And if you're looking at this, you're saying, gosh, you know what? That's sort of like, what do we call those things on that side? What do we call things on that side? Let's see. Let's add this. Noble gases. That last row. And we're saying, well, gosh, the broadest pattern is what's the stuff over there? Starts with an M. What's the stuff over there that starts with an N? Metals. They tend to lose electrons if you lose electrons, do you become positive or negative? Positive. Those big atoms lose electrons and become positive. The nonmetals tend to be smaller. They tend to gain electrons to become anions. So far, all we've done is pretty much Professor Paula Abdul and some patterns on the periodic table. That's it. And noble gases tend to do nothing, tend to not gain or lose electrons. So here's some practice problems that will allow you to apply that. By the way, these are right out of your book. They're right in chapter 3, so you can find the answers there. I'm not going to reveal the answers here, but maybe I'll put these in a little lecture questions there. So I'm going to give you a few hints, and then I'm going to let you do it. If you get the right answer, great. If you don't, come see me in office hours, or let's chat on recitation or something like that. Okay. So it says, hey, you get rubidium and cesium, and there's some other elements in their column. Would you think the ionization energy would be higher or lower than the other similar elements in their column? Now here, which element is likely to lose an electron? Am I talking about the bigger atom or the smaller atom? In every case, should I be trying to identify the bigger atom or the smaller atom? That's the key. Lose an electron. Does that sound like something like a tiny atom would do or a big atom would do? Same thing here. Which of these is more likely to gain an electron? Well, do big atoms want to gain electrons, or do little atoms want to gain electrons? So up here, which is more likely to lose? The larger atom. Which is more likely to gain? Smaller atom. Which is likely to do neither? The noble gases. Helium, neon, argon. If they were ever there in one of these, you go, nope, they don't do it. They don't participate. They're sort of like not even under consideration. Okay, now we have to have this language. Here's one of our first big tasks in Chem 51 is, I need to be able to say the name of these ions. When I have the name of these ions, I have to be able to know the charge and the symbol. There is no other way to go on to chapters 5 through 11 if we don't have this. So I'm starting to put together some tables, the next 2 pages, to say, here's what you have to absolutely have memorized. Now, I've tried to organize it in a way that patterns will emerge, but it's a flashcard for each of these things. So the first few metals look pretty easy. You go, what do we call a sodium ion? We call it a sodium ion. What do we call a silver ion? Silver ion. There's silver, silver ion. What would be a good name for a calcium ion? Calcium ion. We know it's always +2, 2 plus, because it's in that second column, but I go, calcium ion. Now, if we were on a roll here, what would be the good name? What good name for an aluminum ion? Aluminum ion. So some metals are really easy. It becomes a cation. You go, are you talking about aluminum or the aluminum ion? Are you talking about sodium or the sodium ion? The name is the same. We have to be careful. Are we talking about sodium metal or sodium ion? But the actual root name, it's the same. Then remember those metals. There's about 7 metals that can have more than one charge. Turns out they're not the same. If something has a +2 or a +3, it's not the same stuff. The compound's not going to be the same. So there's iron. If somebody says iron, I have to say, wait. Are you talking about iron 2+ or iron 3+? Now, here's the simplest naming scheme. It isn't always used. We'd call iron with a 2+, iron, Roman numeral 2. What would we probably call this one? Iron, Roman numeral 3. So, okay, if somebody says iron 2, I'm thinking it's iron 2 plus. If somebody says iron 3 plus, oh, that's iron 3. That's not that bad. What would be a really good name for copper? And this one? I'll stop the video and let you do this. All right, you did the little quiz, right? You got it right? Oh, you said, Wallace, this is easy. This is copper 1 ion. And this is copper 2 ion. That's not that bad. Okay, there's 7 of these that we kind of have to know can do that. That's not too bad. Then it gets a little bit weird. Dental hygiene folks, when you talk about like what's in a toothpaste, you don't say fluorine in toothpaste, you say fluoride. Hydrogen, when it's an anion, I don't say hydrogen, I say hydride. Similarly, chlorine minus, bromine minus, iodine minus. Fluoride. What do you call table salt? Sodium chloride. You don't say chlorine. Oh, chloride. What would be a good name for this one? Bromide. And this one? Iodide. Oh, okay. That's not too bad. Fluoride, chloride, bromide, iodide. That means that element with a negative charge. It's ion. Oxygen, sulfur, and selenium are in the same column. If oxygen forms a -2, a couple pages back, what did we see the charge was on sulfur? 2-. And selenium is right below sulfur. What would you guess? 2-. Oxide, sulfide, selenide. Now, I'm not going to write ion, but sometimes in the homework it'll say, name the ion. You go, okay, I better say sulfide ion, selenide ion, chloride ion, bromide ion, iodide ion. Nitrogen and phosphorus. Nitrogen is the downstairs neighbor. Phosphorus is the downstairs neighbor. 3-. Nitrogen becomes nitride. Phosphorus ion becomes the phosphide ion. So you go, okay, there's a bunch of anions, all in an ide. I have to memorize the pattern and memorize a little bit the naming scheme. Now, I didn't write these in there because on the very next page, at the bottom of the next page, bromide, chloride, iodide, oxide, sulfur, hydride, nitride, phosphide, selenide. There they are. Now, here's the bad news. Here's our 6 or 7 or 5 elements, metals, that have more than one possible charge. So chromium 2 is chromium 2. Chromium 3 plus is chromium 3. That sounds nice, but there's an old naming scheme that won't go away. If you're a nurse or nutrition and somebody says the patient needs iron supplement, and you go looking in the stock room, the pharmacy, or whatever for iron, it's not going to say iron. I think it's going to say ferrous sulfate. Right there. Ferrous means iron 2 sulfate. So these won't go away. So we have to know this other way of saying this as well. Chromium, chromous or chromic. Copper can be cupric or cuprous, and so on. There's just pure memorization. Now there's one pattern that will help us a little bit. In the old naming scheme, if it's IC or OUS, IC is always the higher charge. And US is always the lower charge. So if somebody says, I memorized, copper's a 2 or a 1. And somebody says cuprous, I go, US. Oh, that's the lower charge. If they see cupric, I go, oh, that's the higher charge, the 2. And your task right now is to start making flashcards. Those charge patterns and these names, all of this has got to be memorized. In chapter 4, you can cheat a little bit. Chapter 5 and 6 and 7, we're done. You won't be able to go any further if you don't have this memorized. All right. There's chapter 3. You can see it's not too bad. There's some cool mechanisms that allowed us to sort of figure out how things worked. And there's a little bit of naming. The second part of chapter 3, we're going to say, okay, well, how do we put these together and make compounds out of them? All right. Thanks for hanging in there. Let me see. I'll flip that page. No, I won't. All right. I'll see you at the next lecture.